Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to have Jairam Mudigunda with us this morning. Jairam is a PhD, a fresh PhD from UT Austin, and where he's currently a postdoctoral fellow. Jairam received his PhD in December 2005 for work on high-performance packet processing systems. He had fellowships from both UT Austin as well as Intel to support his work. And previously, he was a member of technical staff at Bell Labs. And today he's going to tell us about some of his work.
Thank you. Good morning. So today I'm going to talk about how to handle this notorious problem of memory bottleneck in packet processing systems. So let me start with a quick definition of what I mean by packet processing systems. Packet processing system is any system that processes large numbers of internet packets. Not necessarily routers. They could be routers, could be a complex edge router or a relatively simple core router, or for that matter, many end systems fall in this category too. Web servers, transaction servers, network attached storage, all these are good examples. So an ideal platform for these systems should be versatile. So informally, a versatile system is one that achieves two important properties simultaneously. First is ease of programming, and the second is ability to sustain high packet throughputs. So that is, a versatile platform should make it easy to develop a variety of applications, sophisticated applications, that also demand high packet throughput. So this platform, such a versatile platform, is attractive for many variety of reasons. First, it fosters innovation. It does so by making experimentation easy as well as effective. Because these systems are programmable, are easy to program, one can experiment with new ideas. One can develop a prototype relatively quickly and easily. So that shortens the turnaround time between the idea conception and the feedback whether that works or not. These systems also make experimentation effective because they are able to sustain very high packet throughputs. So that lets the experimentation to be carried out at a scale that resembles more realistic deployments. So we have hope that whatever the experimental results are going to hold in practice with a greater certainty. Okay. A versatile system not only makes it easy to develop new applications and services, but it also makes evolving the existing ones easy. So inherently, if a platform is easier to program, it will let you crank out, say, security updates or bug fixes much more often, and rest assured that they are not going to break most of the other fine-grained optimizations that somebody may do today without the programmability. And it also allows the platform, the systems to scale to larger and larger user populations, and also augment functionality as and when required. For all these reasons, it also, such a versatile system also makes it easy to deploy new services with a minimal disruption and also incremental growth. So once a service has been deployed, it can be made available to a handful of people as the user population grows. Because the platform inherently allows modifications easily, can make it scale to larger and larger populations. Okay, so not very surprisingly, the effort Genie that is being funded by NSF and is being worked on at many universities, which is Global Environment for Network Innovation, identifies a versatile platform as a key requirement for advancing the state of the art, not just in research but also in practice. Oh, I see. Yeah. Yeah. Having a versatile platform is good, but it has proved to be pretty difficult to build a versatile platform. Let me start with a little bit of background. The current packet processing systems that process internet packets, can be broadly classified into two categories. The first is based on general purpose processors. These are mostly PCs in many cases. And these systems are extremely easy to program. So they do get one of the two important properties, easy to program part, but they are not known for their high packet throughput. They can't really sustain the high bandwidth links available today, many of them. On the other extreme are systems that are based on application-specific integrated circuits, ASICs, and these systems are quite capable of sustaining very high packet throughputs because most of the processing is done in hardware. But obviously, they're extremely hard to modify. Even a minor addition or a minor bug fix could be extremely difficult. It might even involve, pulling chips out and plugging new chips in. So in the recent past, there is a new class of processors called network processors appeared. They exploit the fact that now the technology allows us to put multiple cores on the same chip. So they are all multi-core chips. And the goal is to bridge the gap between the general purpose processors and ASICs, get best of both worlds. They are supposed to be the versatile platforms that I was talking about. But unfortunately, most of these network processors remain very hard to program. And a main reason for this difficulty comes because of how these architectures, the network processor architectures, chose to handle an important problem, namely memory bottleneck. So memory bottleneck is an important problem in packet processing. It's a problem even for general purpose computing, but it is even more important in packet processing for two reasons. First, it's the primary limitation to achieving high throughputs. So most programmers spend a lot of time trying to handle the overhead of memory access. Secondly, it's getting worse, much faster than it is in general purpose computing. Two factors contribute to this exacerbation. First, the link bandwidths have been growing up. That is, there are more and more packets coming in per unit time that need to be serviced. On the other hand, applications have been becoming increasingly sophisticated. So some of the modern systems like virus scanning require a couple of orders of magnitude more references per packet than traditional IP forwarding. So on the one hand, there are more and more packets coming in. On the other hand, each packet now requires a lot more access. So the problem is getting exacerbated. So this importance of memory bottleneck is not really lost on many of the designers. That's the reason why most of the packet processing systems based in either NPs or on other processes, they include a variety of mechanisms. So often this memory bottleneck is likened to a big brick wall. So it's called memory wall. And let me extend the analogy and classify the techniques into two categories. Hammers that break the wall, they basically exploit the locality, various kinds of locality to reduce the memory access overhead. And ladders, they actually allow you to go over the wall, and they mostly exploit parallelism, some kind of parallelism. Under hammers, there are wide words. Wide words allow you to bring in more than one word at a time when you go to memory, thereby amortizing the cost of going to the memory over larger number of bytes. And result caches will allow you to cache the results of often repeated computation. A good example is a route lookup. So when you perform a route lookup for an address, you save the results in terms of by a mapping, the destination address and the next hop address the packet went to. So when another packet appears with the same destination address, you skip the entire lookup, you just use the results from the result cache. Result caches are useful not just for route lookups, there are other places where you can cache result too. So there is hardware support for result caching, and there is a support for a memory hierarchy that is often exposed to the programmer. And under ladders, hardware multithreading allows one to exploit inter-packet parallelism. Each packet can be assigned to a thread, and when it makes a memory reference and stalls, you switch to a different thread, and thus overlap the computation of one packet with the IO of one or more other packets. So you basically try to find something else interesting to do while the processor is waiting for a memory access. Asynchronous memory is a non-blocking memory. The semantics of load store instructions are slightly different with asynchronous memory. A load doesn't stall. It continues unless the programmer wishes to context switch. Asynchronous memory is pretty useful in exploiting intra-packet parallelism. Within a packet, when you have a bunch of data that need to be read, you can issue all the accesses and then do whatever you could until you are absolutely blocked by the data that you are hoping to get from the memory. Okay, I want to note that one of the very popular hammers, namely regular data caches, is absent here. So most packet processing systems routinely or systematically shun packet data caching for a variety of reasons. Okay, so let me give an example why this powerful hardware with so many hammers and ladders is difficult to program. First, there are many of the mechanisms. The programmer has to figure out what works where and pick the right set of mechanisms that actually maximizes the benefit. And most of these are pretty low level. Like for example, wide words. So the programmer has to manually figure out how wide a reference that he is willing to make. So for that, on the one hand, he has to design the data structure so that more data items that are accessed together fit into one of these wide words. On the other hand, he'll have to manage the registers carefully. Each wide word consumes a larger number of registers, not just one, when they come into the processor. On the other hand, any one of these mechanisms is not sufficient to completely bridge the gap. So oftentimes, programmer has to actually look at more than one schemes, and that is complicated because, again, the relative price performance ratio, as in how much resources a particular mechanism requires and how much effective it is going to be, is something very hard to determine offline, and the programmer cannot guess it easily. To give you a very high level quick example, assume that I am trying to use hardware multithreading and byte words. If I have a bunch of registers, the number of threads I can support over that bunch of registers is going to be high if I ensure that each thread uses up a small number of registers. So what I'm saying is you can use the registers to, if you use carefully the register file, you can actually increase the number of threads. Thereby, you can actually hide the memory access overhead more effectively. On the other hand, if I use wide words, now that pulls the register requirement of each thread the other way. So now you have a trade-off to make, as in, do I make one single thread very effective by using wide words, or do I make each thread somewhat, not so effective, but I'll use a large number of them so that I can hide the memory access overhead. And because these two mechanisms, wide words and multithreading, end up using the same resource, and their effectiveness can vary from program to program, from system to system, depends on the application characteristic, depends on the off-chip memory. The decision as to how much would I stress on one versus the other becomes pretty complicated. Okay, so that is only one level of one direction that makes it hard to program these processes. The other is that most of these mechanisms are fixed in silicon. The provisioning level is fixed in silicon. Again, let me take you a concrete example: hardware multithreading. The number of hardware threads that one can have is pretty much fixed in hardware. So if my application, for whatever reasons, my deployment requires a larger number of threads, I'm out of luck. I have to somehow make use of the threads that I have, somehow improve the effectiveness of each one of them. So in general, what happens is, because the provisioning of all these mechanisms is fixed, most often programmers are left with the difficult task of extracting last ounce of performance from an architecture that is not really suited to the task at hand, deployment at hand. So for my dissertation, I was asking two questions. How can I, the basic goal is to make, achieve versatile platform. So the first question asks, do I really require all these mechanisms? Is there a much smaller subset of these mechanisms that would work as well? And that would simplify programmability, because now the programmer has to deal with a smaller number of alternatives and smaller number of trade-offs consequently. And once I have these mechanisms, how would I provision them? How would I use some common resources? For example, in this area, in this topic, I'm going to focus on chip area. How would I utilize a given amount of chip area to build a processor that involves these two mechanisms and also is versatile? Means the provisioning is just right in a large number of deployments. So here are the basic high-level answers for both questions. For the first questions, what mechanisms, I assembled a set of applications, benchmarks, and collected some traces from the real internet locations, and developed a simulation infrastructure, and did a careful comparative study of many mechanisms. And the answer for the minimal set that simplifies programmability as well as achieves high throughput came out to be data caching and multi-threading. So as I just mentioned in the previous slide, data caching is not used in today's systems at all. And it turns out data caching actually is not only, okay, one of the main reasons, there are many of them, one of the reasons that was often told to me why data caching was not used in any of the packet processing is that there is no locality. Packet processing doesn't exhibit temporal locality, so data caching is of no use. So we found that there indeed was a lot of locality. In fact, data caches obviate all other hammers. If you have data caches, you don't have to worry about wide words, you don't have to worry about result caches. You don't even have to worry about splitting data structures across the exposed memory hierarchy, so on and so forth. But data caching alone didn't really ensure high processor utilizations. Even at a very large amounts of cache, the processor tended to stall a lot. That's primarily because the applications are extremely memory intensive. So on the other hand, okay, so we had to combine, yes. I'll get to it in the next slide. Yep. So on the other hand, if I combine, okay, multi-threading and data caching seems to be good because intuitively they achieve high throughput because they're complementary strengths. On the one hand, multi-threading can help in hiding the miss latencies, means the occasional misses that happen with data caching can be hidden using multi-threading. On the other hand, data caching actually makes multi-threading more effective. That's because of two reasons. First, because of caches, now each thread runs for a longer duration. So the number of context switches go down. That means I'm amortizing the context switch overhead over longer run lengths. So data caching automatically extends the run lengths because most of the loads come from the cache itself, so the processor doesn't stall. If the processor doesn't stall, you just continue. Yes. Yes, that's precisely what I would do in the next question. So, okay, I determine qualitatively that these are the two things that I would like because they are getting me the performance. They are also easy to program compared to the example that I gave you. Caching is transparent to begin with, and caching also transparent to the programmers and compilers. They don't have to do anything. And on the other hand, the caching makes multi-threading easier to use. That's because one of the tough things that you do when you're dealing with hardware multi-threading at a raw level is to figure out when to context switch out. So the decision where to insert a context switch depends on several factors. In fact, so you would want to issue as many loads as possible before you context switch out. Of course, the same trade-off that I was talking about. And also sometimes in some applications you can insert context switches intelligently so that the data brought in by one thread can be used by the other. But for that, you have to context switch out at the right time. So context switching is actually done by hand and it consumes a lot of effort today. And with data caching, if you automate that part and assume that I switch and I miss blindly, because that is the long latency operation, what I showed was that it actually gets most of the performance of a hand-tuned context switch placement. So if I have these two mechanisms, it simplifies programmability, because now all that I am requiring is a programmer write a piece of code that is that's just thread safe. Okay, so coming to the question Ratul has, how do I provision them? So the same trade-off as in both of them require some common resource, namely chip area here. And can I provision them so that the resulting processor is versatile? Okay. So I'm going to focus on the second part, and this is how I organize my rest of my talk. If you will, there are two talklets that I'm going to do. The first is it makes a case for malleability. What I mean by malleability is an architecture that allows each deployment to trade off the cache capacity and number of threads at deployment time, in fact at runtime too. To make a case, I'll make 2 points. First, I'll show that the preferred thread cache combination varies across deployments. There are many factors that influence this balance. And secondly, I would show that if an architecture can adapt to these variations, that results in a lot of throughput gains. Then I'll focus on the malleable architectures. I'll present the details and then the experimental results, and conclude and discuss a little bit of future work. Okay. So here are the applications that I studied. So before I actually get to my first talklet, let me give an overview of the experimental setup. So these are the applications that I studied. So these they span the typical steps that are done in many packet processing systems. You verify the packet and then classify them into flows and look up the next hop and do some processing, and finally send them out using a link scheduler. So is this answering your previous question? Okay, sure, yeah. Stream 4, you can see that as a TCP receive side processing. That is done in an intrusion detection system. So what they do is they monitor the ongoing TCP flows, they construct the byte stream out of it, and they look for virus signatures out of it. CAST is an encryption scheme that's used in most VPN kind of applications. Okay, so there were a couple of benchmarks that were developed for packet processing systems, NetBench and ComBench. So this set of applications includes pretty much most of the applications from those two sets. And also there is this network processor forum that came up with functionality that would be appropriate for benchmarking. So this does cover that functionality also. Okay, I run these applications, I drive them with traces collected along the internet hierarchy. I collected, I downloaded most of these from NLANR, and a few came from UNC also. But I'm going to focus on one edge trace and one core trace. And that's because most of the quantitative results, these two traces form the extremes, and qualitative conclusions did not change much from trace to trace. Built wherever necessary the route tables with route view prefixes published by route views. And I run these applications on an enhanced version of Simple Scalar. Simple Scalar is an instruction emulator from University of Wisconsin. I added a little bit of functionality so that it generates what I call an execution trace. So what it does is, for each packet, it logs all the ALU ops, all the memory accesses made, which address it went, how many bytes were accessed. And the trace is separated into blocks. I use this execution trace to drive a discrete event simulator that models a multi-threaded, multi-core processors. It's just bunch of programmable process slapped to it. They actually simplified each core really. Those cores are nowhere close to the capabilities of the regular general purpose processors. They're very simple. They don't have, for example, out of order issue. They don't have multiple functional units. They have a single in order. I'll actually show you this. So this is the system model that I'm assuming. So I have a number of small cores on a chip, and each core looks like this. It's very simple. This is modeled again based on the kind of cores that I found in network processors. It has a replicated register file here, and the data cache is the regular data cache that I determined to be useful, and I assume an instruction store. So there is no instruction fetch logic, nothing. The entire code resides in the processor, and it has a simple in-order single issue pipeline, no branch prediction, no fancy mechanisms at all. So that way you could fit many cores on the chip. So all these cores use one off-chip memory level. I assume this is the model that I'm working with. So all these cores go through the same access mechanism to the same off-chip memory. So now let me come to my first talklet. The question I had was how to provision. The question I have is, if I'm given a small amount of area, or rather a given amount of area, how would I use it to split among 3 different dimensions? How many cores would I put on it? How much cache would each core have? How many threads each core would support? Is this the question that you are getting at? Okay, so the goal is again versatility. As I mentioned, versatility means it should perform well across a spectrum of deployments. Let me make my notion of deployment a little bit more concrete also. Deployment basically captures the operating circumstances for one of these processors. So that is a description of application, that is the code that the processor is running, and the packet traffic that it is seeing. That determines how large the data structures get and how the access patterns themselves are. And these two, memory latency and memory bandwidth, capture the memory subsystem that the processor is working with. The latency and bandwidth are the two main things. Sure. Yeah. No, how much cache would I build? Oh, I have a chip area. Now I am trying to come up with a configuration. Yeah. No, that's what I want to answer actually. Yeah. So, okay. So what I would ideally like is a processor that would allow me to not even answer this question. Means it should give me some facilities whereby I can pick the right number of cores, the right amount of threading, and the right amount of caching per core. But obviously that is not possible because execution pipelines are fixed. You can't reclaim the area given to an execution pipeline for other purposes. But what we could do is to actually fix the number of cores, but allow the number of threads and cache capacity to be traded off. So what makes this a plausible architecture is the observation that at some level of abstraction, both threads and hardware cache, both are storage, both are memory that are supposed to be fast and close to the core. Only thing is that they are used differently for different purposes. And one, I'm using it to hide memory latency by exploiting parallelism. On the other hand, when I use it caching, I'm trying to use it to hold on to data that I think is important, would be accessed in the immediate future, and hence I'm reducing the access latency. So this is the kind of architecture that I would like to pursue and see. So I have the same fixed simple pipeline. I have the instruction store, and now instead of register file and data cache, I have a malleable storage that can be partitioned by each deployment between number of threads and amount of cache. Okay, so what I'll do is, first I'll show that this kind of an architecture is what is preferred by different applications. For this, I'm going to do a simple experiment. I'm assuming that I have 16 thread equivalents of chip area, means the amount of area that I'm working with allows me to construct 16 register files or 16 hardware threads. And for each application, I'll vary the number of the amount of area that I give to threads and cache from 1 to 16 and compute and figure out the combination that maximizes the throughput for that application. Okay. So this is how it looks. So the blue bars here are the number of threads, means how each application split the available area between number of threads, that is how much it is using to exploit parallelism and how much it is using to exploit locality. The main point, qualitative point I would like to make here is that the balance varies all over the place. Means different applications prefer different combinations. Yes. So most of these cases, making a program multi-thread is fairly easy. That's because I am looking at multi-threading for packet by packet. Means, let's suppose you give me what happens on a code that processes a single packet. So I write a simple glue on both sides, which basically takes a packet from the interface / trace, and then forks off a thread, and then that thread runs the code that you had given me. So only extra modification that I had to do is to protect the shared memory. Means if there is a modification that is happening to any data item, I place it under locks for correctness reasons. So that's how I multi-threadize. There is the number of threads it spawns varies. Sure, it might, but I considered all possible combinations anyway. So here I can have any application can choose to run with either 1 all the way to 16 threads, and I looked at all possible. 16 is the max amount of area that I have, so that determines the max number of threads that I can. Yes. Good question. I'll get to it in the next 2 slides. Yeah, so the question that you are asking is how important it is that I actually strike that balance so precisely. Would it be okay if I am halfway? Yeah, I'm assuming. No, I'm assuming that I have amount of chip area. I can build different kind of processes, different number of threads. So for each experiment, I assume a processor that has, say for example, I'm looking at 1 thread and the rest for cache. So I simulate a processor that has 1 register file, and I figure out how much cache that can be fit into the remaining area, and I simulate. So next experiment would be I replicate register file twice, and then I reduce the corresponding cache size, and then run again. No, actually that's a good question too. I'm not doing it because the main reason why I'm using threads is to hide memory latency. I'm not worried about ILP. In fact, there is a study that, so I think in the general sense what happens is if you have 2 threads, you would probably like to have a more number of functional units so that these 2 threads can run. This is not exactly like SMT because here I'm using coarse-grained switching. So in SMT, they are finely interleaved. So what I'm doing here, the model that I have in mind is that a thread runs and it keeps running until it misses in the cache. And that's when I spend a little bit of context switch overhead or swap the next thread in. So this is more coarse-grained than SMT. So the pipeline is being time shared. Oh, the difference is that at any point in time, if you take a snapshot and see, there is only 1 thread that is quote unquote running. There is only 1 thread that has any instructions that are in flight. Yeah, but if in SMT you take a snapshot, you might see more than 1 thread in flight. Yeah, so that's the difference. Okay.
But so, you're finer grained, like you're not having like an operating
no,
thread.
No, I'm assuming that.
Finer grained than that.
Yeah, hardware, you see, context switch is an instruction. So when I execute context switch, it essentially swaps the register file that is firing the pipeline, that is driving the pipeline. That's all. So it's as low as 2 cycles latency.
But there are not like going fast.
Oh, I see. I take it back. Yeah, as in the hardware detects when to context switch, and the hardware does. I'm not assuming there is no operating system, there is no virtual memory, there is nothing of that sort. Yes, switches. Yes. Yeah. If the other thread is ready, otherwise it stops. Yeah. Yes, single core, and I have.
So are you exploring the trade-off?
Yes. But how many would I have cache heavy processor cores, and how many would I have thread heavy core? So the question at an abstract level still stays, as in how cache heavy I make a cache heavy core, how thread heavy I make a thread heavy core. Would I have 1 thread or 2 threads? At this level, no. At this level, no. Actually, I do take into account the opportunity cost. You can't arbitrarily see. If I don't have any penalty in terms of the area that I use, if I am looking at a single core, I can make it arbitrarily big. In theory, of course, it slows down for a variety of other reasons. But in theory, I can make it arbitrarily big and give it a large number of threads and a large amount of cache. So all deployments, all applications are happy. But if I do it, what happens is that a single core becomes so large that you would have had opportunity cost in terms of the number of cores you could fit on a given amount of area. So you would lose out on the number of processor cores itself. So I do actually study that trade-off, and I'll show you. Am I coming close to what you asked? Sure. Here, yeah, this is the 16 thread equivalence. The total amount of area that I have available. That is, so here the purpose is to show that there are some application characteristics that favor one over the other, and that varies all over. So the point here I'm making is qualitative, as in the balance can vary and vary significantly. Okay, let me actually explain quickly why that varies. So these 3 applications, CAST is an encryption scheme, checksum is the TCP IP checksum, and MD5 is the message digest. They have very little cacheable data. They actually scan through the packet, and that's why they benefit very little from cache, and that's why they actually choose very little area for cache and use most of the area for threads. And the other extreme are port scan and DRR. Port scan and DRR both involve data that gets modified on every packet. For example, DRR is a tight loop that runs on active flows, means the set of flows that have at least one outstanding packet, and it keeps decrementing a counter. So that decrementing counter should be done in mutual exclusion, so that prevents it from using a large number of threads. So it uses most of the area for cache. Pardon? Non-temporal load. Yes. Yeah. So because it scans through the packet, it doesn't go through. It cannot utilize cache even if it is there. I see. Agreed. That's a good point. So in this experiment, though, I'm running the same application on all the threads. Yes, that's a good point. Yes. Okay. So we have seen that application characteristics can influence the balance between threads and cache. Now I'll look at how the packet traffic itself can influence, and also how the memory subsystem can influence. So here these 4 bars are for one application, classify, and when I drove it with trace ANL. And I keep everything else constant, I change the memory access latency. It goes from 50 cycles all the way to 300 cycles. As you can see, here at 50 cycles it's cache heavy. It uses 8 out of 16, 12 out of 16 for cache and only 4 threads. As the access latency increases to 3, it flips. It becomes actually, it uses bulk of the space for threads. So again, the qualitative point from this example I'm trying to make is that packet trace can have a significant influence in what you would stress, locality or parallelism. Sorry, not packet trace. The memory access latency can have a significant influence. So what I would do is, I'll now actually run the same application, same setup with a different trace MRA. This is core. So if you compare the bars for the same memory access latency, you can see that MRA actually stresses parallelism more than ANL. That's because MRA is towards the core, and most data structures, the working set sizes actually grow with the number of flows that are simultaneously active, and core traces, because they aggregate traffic over a larger amount of internet, they have more flows. Okay. So again, the point that I'm making here is that there are all these factors that influence the balance between threads and cache. So coming to the sensitivity question, what I would do now is, I would assume that I can actually build a processor, malleable processor, ideal malleable processor, has no performance penalties. It will magically switch between register files and data caches. And I'll see how much performance I would gain if I have that kind of a processor. So in a way, I'm answering the flip side of the question, sensitivity question. If this is large, I would say it is important for you to pick the right balance. If it is small, I would say it's not. Okay, so what I did was I took IXP 2800, which is a state-of-the-art network processor from Intel, and I measured its area, and I formulated and solved 2 optimization problems. Here, I assume that the processors are going to be built using a fixed amount of data cache and fixed amount of fixed number of register files, and I solved the optimization problem to determine the configuration that maximizes the versatility. So I have 6 cores, and each has 7 thread equivalents of each has 7 threads, and 45 thread equivalents of area is devoted to cache. On the other hand, IXP 2800 takes one extreme approach. It has 16 cores, 8 threads, and absolutely no cache. So I also computed another optimal combination. This is the malleable one. Here I am assuming that I have a malleable storage within each core, and the question is how big the malleable storage needs to be. It needs, for this particular set of data, the area and the applications and the memory access latencies and so on and so forth, it turns out that it needs to be 26 thread equivalents. Yeah, so there are a variety of reasons. It depends on who you talk to. One is there is no locality. That's the belief. So any area that you give to chip area you give to data cache is a waste. So that's one. Secondly, some people said that data caches are not required because most applications you can use result caches, means for example route caches, and there is very little effect of data cache on top of it. A result cache can be done in software also. And there are other reasons, like for example, some people said that all packet processing systems must be provisioned for worst case traffic. Data caches are average case. You can't really provision a system or argue about it if you have a data cache. So I looked at the locality part is done. I showed that there exists locality and it's actually impressive. And second, I showed that data caches actually come very close or even beat result caches in most cases. That's actually an interesting observation for myself. In one case, you are caching the data that is used to compute. The other, you are caching the result itself. But it still seems like data caches actually do pretty well. And the third argument, the worst case provisioning, seems to me is pretty. Two things about it. Whatever is the worst case traffic they talk about is worst case traffic with respect to route lookup. All that they say is that the destination addresses need to be randomly generated. Actually, real worst case traffic happens if every packet carries IP options. That's when most of the routers actually crash. Okay. So that is a misnomer to begin with. And what I can show is that even with that worst case traffic, data caching actually automatically figures out that the top layers of the trie usually migrate to the data cache, and it's as good as what you had done with a static provisioning anyway. So I don't believe there is no reason why there shouldn't be data cache. So I talked to Intel people, and they told me this actually verbatim, a politically correct statement. So they said we are going to include a cache, but we don't know when and where and how. So they do buy this part. No. Mix of what I call deployments. So deployment is a combination of application and the packet traffic it is seeing and the memory subsystem it is working. So I have a large number of them. So I have 2 dimensions now. So for each, okay, let me stop here and see. Did I answer your question at least somewhat?
Yeah.
Okay.
I was just wondering if there is a higher amount of
Uh-huh.
variability.
Yep. Not just applications. So it's actually optimizing it across all different operating circumstances a processor might find. My goal is to come up with a configuration that works reasonably well. So I can actually get into detail. What I did was I had this absolute upper bound and I tried to minimize the loss to it. Means the absolute upper bound is given an amount of area, you can pick the number of cores and how each core looks, and that is the best that you can do given an area for a given deployment. And that's my upper bound. So for each fixed configuration, I can measure how much the loss is with respect to this upper bound. So I was trying to minimize the loss. I can actually get into more detail. Okay. So let me explain this plot a little bit in detail. How am I doing? I'm fine. Okay. So here, these blue bars are probability distribution function over the deployment space. That is, for a given amount of improvements, this bar denotes what fraction of deployments saw that improvement in packet throughput. So here I am comparing ideal malleable versus IXP 2800. So this improvements is what the ideal malleable could get over top of IXP 2800. The red line there is 1 minus the cumulative distribution. That is, for a given amount of performance improvement, it is showing the fraction of deployments that saw at least that much of performance improvement. Okay, so I'm going to use these plots, more of these. So I just want to make sure that I'm making sense here. Sure. Yeah. You have a question? Yeah, my goal is to utilize the area effectively. Yes. Okay. So the point is that in about 1/4 of the deployments, the ideal malleable can improve the throughput by 4-fold, 400%. That is very significant. And but what I'm doing here is I'm comparing a commercial processor that is not necessarily optimal to an ideal malleable processor. So instead, what I should do to make a case for malleability, case for changing this trade-off dynamically, I should compare to the best possible fixed architecture. So that's what I do the next. Yeah, I would lose. Yes, that's because of the number of cores. I have smaller number of cores. So there are some applications that could actually use a large number of cores. Each. So IXP 2800 has 16 cores, 8 threads each, and no cache. My processor, this ideal malleable, has only 9 cores. Each is much larger core. So if a deployment actually benefits from a larger number of cores, I would support. Okay. I am comparing absolute cores times. I would see differences. Yeah. In one case, you are overlapping computation also. Yeah, it's not just the product that matters. It's the split that matters. Yes. Okay. So to make a case for malleability, I compare it with the best possible fixed architecture. And again, the same plot. Blue bars are PDF. The red line is 1 minus CDF. And the point I want to make is, I still see very significant performance improvements if I have malleability. I see about 60% improvement in throughputs and about 1/3 of the deployments. So this is good. So okay, here is a summary recap until now. So I looked at what are the mechanisms that I would require. I said I don't need all these different mechanisms. I just need 2, data caching and multi-threading. And the second question, and then I showed you that we need malleability in the architecture. That is, the architecture should be able to trade off how each deployment stresses locality versus parallelism. That is, the data caching versus number of threads. And now the question is, can we really build such a processor? Okay. But building such a processor is actually pretty challenging. This kind of a malleable processor is pretty challenging. That's basically because the access patterns to register files and data caches are pretty different. Registers are accessed more often than data cache. Registers are accessed up to 3 times a cycle. Every instruction can make 2 reads and 1 write. Whereas data cache access happens only every 4th or 5th cycle sometimes. And also register cache access need to be file access need to be very fast. That's because the pipeline clock frequency depends on how fast the register file is. On the other hand, data caching you can live with a slightly longer latencies. So these 2 structures, register files and data caches, are built inherently differently at circuit level. On the one hand, register files are optimized for high bandwidth, low latency access. In the process, they sacrifice capacity. They have fewer number of bits. On the other hand, data caches take the exactly opposite approach. They maximize the number of bits, but they sacrifice the latency and the bandwidth to the structure. So to give you a concrete feel, if I take the same 26 thread equivalents that I worked with before, the 926 combination, and use the entire thing to build a register file, I would use the entire thing to build a register file. I would have lost about 2/3 of the capacity that I could have fit in had I gone with the data caching route. Means had I used the same 26 thread equivalents, I would have gotten about 3 times more capacity. It's exactly the same the other way around also. If I maximize for bandwidth, as in if I build register, sorry, I'm doing the same thing. If I max for capacity, I would have lost about 2/3 of the bandwidth. Okay. So what we need is an architectural technique. We still have to live with storage structures that are built differently. Now we have to do something intelligent so that we can achieve malleability. Okay, so here is the high-level architecture. I'll start with a clean slate, and here is the simple 5-stage in-order pipeline. And I am taking the route that I use most of the area that is available to me to build capacity. That is, I'm trying to put as many bits as I possibly can. So I build a big data cache. This is definitely not to scale. It uses up the most of the area. Okay. So now what I'll assume is that this data cache can be partitioned into 2 logical partitions. The one is used to pin all the registers for all the threads, and the other is used like a regular cache. So now I can achieve malleability by simply shifting the partition. I move it this way, I have more threads. I move it this way, I have more threads because I have larger number of registers that can be pinned, and vice versa. So now the challenge is, because data caches, as I said, is low bandwidth and high latency structures, I need to somehow supply the data to the pipeline at the speeds and at the bandwidths that the pipeline requires. So that is the job of this MRC. I'll explain what MRC stands for. So what MRC does is it accesses the pinned registers, and it supplies the access from pipeline, operand reads and the write backs. So now, I'll make 2 simple observations. First, MRC is not going to really store anything. All the registers are actually going to be stored here. So whatever area that I am devoting to MRC is an overhead in terms of the entire capacity that I have. So the larger this becomes, the smaller the data cache needs to become. The smaller the data cache, the smaller the degree of malleability I have. It cannot sustain the entire range between 1 and 26 in my example before. So if you see the job of MRC, the second point is this. The job of MRC is to extract bandwidth and reduce the latency of a slower memory and a larger memory. So this is looking like a very much regular memory hierarchy problem. So I have a small, large memory there, and what MRC needs to do is to actually extract bandwidth and speed out of it so that this runs fast enough. So this is essentially a memory hierarchy problem. So we can do two things. We can use the two basic principles that most memory hierarchy systems use, caching and prefetching. So I can make this look like a cache, a register cache. That's what MRC is actually, multi-ported register cache. Or I can make it a more double buffered prefetcher kind of thing. So let me actually explain what I mean by those two and say why those simple techniques cannot work here. So register caching, as I just said, it is going to look like I'll implement my MRC as a simple register cache. I'll run LRU over it. So when a pipeline access comes and the corresponding register is not found, the pipeline stalls. You go to the pinned registers in the cache, data cache, bring it back, supply it, and the pipeline continues. On the other hand, prefetching can be implemented if I have two buffers. I have MRC as two register files, and one register file drives the pipeline. It holds all the registers for the currently running thread, and while the current thread is running, you fill the registers for the next thread that is going to run into the second buffer, and on a context switch you simply swap. Okay. So these two, both of these actually don't use the area efficiently. Both of these would require, in my 26 thread equivalent example, more than 13 or so for thread equivalents for MRC. So to see, so what I did was I computed the area required for these two schemes. If I were to make sure that the thread heavy deployments, all the deployments that wanted more than half of 26 as threads, if they were to perform within 10% of the ideal malleable that I studied to make my case, if I were to restrict the loss to within 10%, what should be the area? And that comes out to be about more than 50%. And if I indeed go that route, the other half of the deployments that are cache heavy deployments suffer badly. They lose 50 to 85% of performance. And in fact, this happens the same way. Means if you really reduce MRC size, cache heavy deployments perform very well, but the thread heavy deployments suffer. So the basic point is that these schemes cannot be used, are not area efficient to realize my malleability. They make MRC too big. And let me give you a qualitative, intuitive reason why. Register cache uses up most of the area, again, to build lots of capacity. It builds lots of bits. On the other hand, register double buffering used up lots of area to provision bandwidth. Okay, let me get a little bit more detail. Register cache required a lot of capacity because of two reasons. One, there is a little locality in register access. That means there are working set sizes are large. On the other hand, each miss actually is expensive. Each miss stalls the pipeline. So if you want high hit rates and large working sets, you need large cache capacity. Okay. And also another point is working set size grows linearly with number of threads. There is absolutely no share. Okay. On the other hand, register double buffering needed lots of area for bandwidth, because for the pipeline to not stall, what we need to do is, while the current thread is running, you should finish bringing in all the registers, all the 64 registers by the time the current thread stops. If the current thread is going to stop relatively quickly, it's not really going to run, say, for hundreds of cycles. It's going to stop, say, 5 cycles. So you have 5 cycles of time to get 64 registers in here. So that means the number of registers you need to fetch per cycle actually grows inversely with the run lengths. Means how long the threads run. And most of these threads actually run for a fairly small number of cycles. So the cache, register double buffering needed lots of bandwidth. And this lots of bandwidth comes at the expense of area, because bandwidth in hardware structures can be provisioned by means of either extra ports or extra banks, and both of them cost area. Okay, so again, the main point is the simple techniques, register caching and register double buffering, are not area efficient. One needs a lot of area to build a lot of capacity. The other needs a lot of area to provision a lot of bandwidth. Okay. So what can we do? So if we take a step back and see why each one of these failed, we can actually derive a lesson for ourselves. Caching is good because it brought in only those registers that are required, because it knows if it is fetching a register, it's guaranteed to be used. The pipeline already stalled. But it waits too long, the pipeline already stalled, you paid the penalty anyway. And the double buffering does exactly the opposite. It solves the first problem. It It eliminates all the stalls because it brings in registers very early, but it actually sacrifices the accuracy as to what registers are required. So it brings in all the registers, so it leads to a lot of bandwidth. So if I want best of both worlds, what I need is a scheme that brings in only those registers that are required. So this leads to the basic principle of predictive prefetching. So what I want is MRC to be able to predict what registers the next thread requires and bring in only those registers and let the next thread run. So the key idea I use to implement predictive prefetching is that the current program counter where the next thread is going to run predicts the set of registers that that thread would use when it starts to run. And this is intuitively going to hold because of two reasons. One, I have a mapping between PC and the sequence of instructions to follow, and that is shown to be working. That is the branch prediction, trace scheduling, all these things. So if you know the PC, you know with a reasonable accuracy what instructions you are going to execute in the immediate future. But once you know the sequence of instructions, you also know the sequence of registers, because the registers that are going to be accessed are hard-coded into instructions. So this should work. So this is the high-level architecture of my malleable processor core. So I have a big data cache. I split it into 4 banks, and I partitioned it between the thread-specific data here and the regular caching here. And the thread-specific data has 2 components now. These are all the registers for each of the threads, and I also have the predictor tables. Yes. No, actually, PC would have told you which way to go also. See, branch prediction, if you have a PC, I have a whiteboard, okay. If you have a PC, and you know until the next branch you are for sure going to work. The branches are highly correlated. If it had taken this way, the then part, it is likely to take the then part also. That is the branch prediction. So if you simply see the path that you are going to take from a given PC, it's highly correlated. The same path is again and again taken. Okay. So I have the predictor tables also in this. So the operation is simple. You have 2 register files, and in one of them is going to run the pipeline. The other is going to be filled by the predictive prefetcher with the registers required for the next thread to run, with only those registers that are required. So let me quickly say what are all these. This cache scheduler is going to receive on each cycle a different set of requests, and it schedules in such a way that it gets the maximum number of them satisfied. It gets the register prefetch requests from the predictive prefetcher. It gets all the misses that might happen, means the predictive prefetcher might fail to predict some of them, and the pipeline needs it. So those demand fetches come here, and the load stores come here. Load stores from the pipeline. Okay. So having explained the high-level architecture, let me evaluate the predictor itself first. Let me say that it is accurate. Accurate as in it prefetches a register if and only if it is required. So I'll show that it prefetches all the registers that are required, and I'll also show that prefetches only those registers that are required. Sure. Okay. And then I'll show that the overheads in terms of space, the chip area required, as well as chip area, as in here actually I talk about the maximum number of predictor entries and also the bandwidth between the MRC and data. So this is a simple experiment. So what I did was, for each application I recorded the maximum miss rate that had been ever seen over all the deployments that application was in. And the main point I want to make here is that the predictive prefetcher brings in almost all the registers required pretty efficiently. The only one that has the highest miss rate here is 1.8%, and that's fairly low. Okay. So now I compare it with the Oracle. I'll see how many more registers that are useless that I brought in. So here the Oracle knows exactly the set of registers that are required, and it brings in only those. And the white bar here shows the number of prefetches that were done by my scheme. So the main point I want to again make here is that it compares favorably with the Oracle. So it's bringing in registers only that are required. So having shown the accuracy, let me show the predictor table sizes. No, it wouldn't. Actually, I have done that experimentation. I tried to guess what are the hot registers. Because I am not assuming compiler would give me any extra help at all. That is one route completely I can take. Compiler tells me every few instructions, okay, these are the subset of registers I would use in the next 10 instructions. Something like that I can imagine. If you don't imagine that kind of a thing, you can still guess some of the hot registers based on calling conventions. You know stack pointer is going to be accessed very often. You know which one of the registers is stack pointer. So you bring in only those, like for example, argument registers. And then how would I use it? I would need to again input the table between PC and the registers required, right? So now if I could discover it, and I could discover it with relatively low overhead, why wouldn't I do it? Sure, I actually assumed those things. I actually studied all the simple schemes that one could come up with. For example, most of these applications don't use floating point registers right away. I can discount 32 out of 64. And out of the other also I can profile and say, oh, there are about 16 registers that are hot. Sure. Yeah, if I can take this offline, I actually did this kind of profiling also. I saw what is the top 5 or top 6 hot registers that a program uses. That is the only information I get from the compiler. Let's suppose I ran it and I use it. Even that actually stalls the processor a lot. So that 5% of the top 5 hot registers accounts for only about 50 to 60% of that. So if you want to go to 99 with that kind of a static prediction, you needed very high bandwidths anyway. It pretty much approaches the blind double buffering that I was talking about. Okay. So let me hurry up. So the simple point I want to make here is the predictor table sizes are fairly manageable. And let me skip the intuitive explanation. Okay, so the intuitive explanation is that to begin with, most of the code sizes are fairly small, and only a fraction of that actually is traversed most of the time, because in packet processing applications, particularly these ones, there are lots of error conditions that get really executed. And within that fraction, the path also, only load stores cause the context switch. So you are interested in only load stores. Even within that load stores, you have only a small number of loads and stores that cause misses. So you end up with a small number of entries in the table. Okay, here I'm looking at what kind of bandwidth the MRC requires. I'm comparing it with the blind prefetching. So again, these are the blind prefetching, the double buffering that I showed before. The blue is what the predictive prefetcher requires. The point is that I require fairly small and manageable bandwidth. Okay, so now what I do is I look at the entire processor. I'll compare it with 4 different processors. So I take 926 configuration and instantiate my architecture, and I'll compare it with the ideal malleable XP2800 fixed top, these 3 things that I talked about before, and also with the fully configurable hypothetical processor. So that is the one that lets you choose even the number of cores. So okay, here is how the predictive prefetching architecture compares with ideal malleable. This is the same plot. Blue lines are PDF, red is 1 minus CPF. So in more than 90% of the deployments, this architecture performs within 3% of the ideal. And with the IXP2800, it gets pretty much all the benefits of what the ideal malleable got, because we are within 3%. So again, in about 25%, I see 4-fold improvement. And with respect to fixed opt, the 6745 configuration, again I get all the benefits that I showed you with respect to ideal malleable before, and I get 1/3 in 60%. So this is interesting. So this is the fully configurable. This is in a way, if you are given a sea of gates, like an FPGA without its restrictions. What could you have done versus how close malleable architecture is? So in about 3/4 we'll get, say, within 20%, which to me seems pretty good. Okay. So here is the summary. So I argued versatility is important, but it is hard. And one of the reasons that that makes these platforms hard to program is memory bottleneck. I showed that malleability is required, and I showed an architecture that can actually achieve this malleability, and I showed that there are impressive performance gains to get. And let me take 5 minutes and talk about my future work. Okay. So I organized my future work into 2 major lines. One is concerned with the packet processing systems and networking in general. The other is more general applicability. So the ease of programming part. So within packet processing, I want to focus on ease of programming as well as ease of deployment. Under ease of programming, the next question I would like to answer is how do I exercise malleability? This probably comes to part of your question too. And now I have a common resource that can be shared for threads and cache. How would I split it? I still have something that the example that I gave you before, wide word sources. Yes, that is what I'm working on now. So if you will, actually what I tried to do until now is what should the hardware support? How would I exercise part is what I'm working on now. So if I can do that, it's going to simplify the programmability even further. Now programmers can simply not care about the representative trace the way that they do now. And it also makes the system very robust to fluctuations. And so if somebody bombards me with all random IP addresses, I would maximize throughput. If there is locality within the packet stream, I would also minimize the response time. On the other hand, another aspect, another building block, if you will, of all packet processing systems is load distribution. So you have a bunch of requests coming in, like packets or HTTP requests, and you have a bunch of processors. And you need to distribute. And there are lots of schemes proposed, but most of them are implemented on software in one of the redirector boxes kind of architectures. What I want to know is there a common subset of facilities, if supported in a multi-core processor, would simplify the load distribution? So I want to start, again, from first principles, and I want to ask the question, what are the circumstances where I would choose to pin a flow to a processor versus I don't care and I send the packets? Depends on variety of factors. And if I can actually automate this decision, that simplifies the general packet processing development quite a bit. Because whether you do flow pinning or not, today is tightly coupled into the way that the application itself is written and the data is managed, everything. So on the ease of deployment part, these platforms need to be virtualized on the same lines as the slice in Planet Lab, if you are aware. If I can virtualize these high performance systems, if there is any, provide some architectural support for efficient virtualization that can also ensure performance guarantees, I can simplify deployment because I can now roll out experimental versions and run them along with the production versions and slowly improve. As the system becomes more stable, I allocate more resources and scale the new version. So I would like to look at if there are any architectural mechanisms that would support virtualization. Oops. Okay. On a more general applicability, I believe that multi-cores are here to stay because single-core processors are beginning to be limited by a variety of fundamental factors, like wire delay, for example. And the general belief is that there are lots of server systems, many so-called business systems with lots of parallel requests coming in are natural candidates for these multi-core systems. But from my experience, I can say that though there is a lot of parallelism, unless the architecture supports some facilities, it's hard to exploit that parallelism or make it easy to use the multi-core processors. So a more broader theme that I would like to pursue is how do I create versatile platforms out of multi-core systems for the request processing class of applications in general. Like for example, one of the observations that I made that there is the locality parallelism trade-off is significant, and it happens in packet processing is not very specific to packet processing in any sense. So any throughput system, you have lambda equal to n over t. Lambda is the throughput, n is the number of simultaneous requests you are serving, t is the time each request takes. You can increase lambda either by increasing n or by decreasing t. But in most practical systems, either increasing n or decreasing t require the same resource. Example at a different level, not packet processing, is web and other transaction servers. So you have requests coming in. The main memory can be used to either to create lots of OS threads, or you can use it to cache some of the objects that you just sent out. And splitting it the right way would make systems more robust, and also you could actually minimize the response time for any given throughput. Yes, given the throughput that you need to sustain, you can also minimize the response time. But if you look at most of the current research, it either focuses on throughput. There are lots of papers that talk about how can I use the main memory to create lots of threads, or there are systems that focus on reducing T. How quickly can I serve? Most of the web caching kind of work. So that brings me to the conclusion.